My name is Tianxi, and this is a collaborative work with Erman Ade, Emery Alamus, Ming Li, and Pan Li. So first is about the motivation of this work. So nowadays, it is very common for a database owner or database curator to share their database with companies for the purpose of do-it-yourself calculation and customized advertisement, or they may share the database to research institutions for the purpose of collaborative research. However, there will be security and privacy concern in this process. For example, some employee in the company may unauthorizedly redistribute the received database and make a pirate copy in order to gain some illegal profit. Or some employee in the company may be just curious about what is the salary of a specific user in the database. And the exact same security and privacy concern may also happen in the realm of the research institution. So in the process of sharing a database or releasing database, the database owner wants to not only prevent illegal redistribution and also protect the data privacy. So to solve these two goals, we will resort to two key techniques. The first is database fingerprinting. The second one is differential privacy. So for the first technique, fingerprint is essentially imperceptible marks injected into the database. It will only cost slightly change to the database utility, so it can be used to prevent illegal redistribution, identify the source of data leakage, and also provide evidence to let the database owner to trace the traitors who should be responsible for the data leakage. And also for the differential privacy, it is a classical tool to obfuscate individuals' data and also defend against some adversarial attacks. However, these two goals are essentially orthogonal, which means to achieve liability, prevent illegal redistribution, you need to insert different marks into the shared databases. So all the receivers will get a different copy of the database. However, for the privacy, you only need to inject the noise once using whatever data sanitization technique. So all the receivers will receive the exact same database. And also, both technique, fingerprinting, and differential privacy will compromise the database utility. And a naive method like sequentially compose these two techniques together, for example, add fingerprinting first and then followed by data sanitization with DP guarantee, will always lead to a suboptimal data utility. So in this work, we will develop a unified scheme to achieve high database utility, and this scheme is called privacy-preserving database fingerprinting. So this is the overall workflow of our scheme. We have database owner. She wants to share different copies to different service providers. And when she shares the database, she will insert some unique fingerprint marks into the dataset. These marks are random binary bits. And the fingerprint insertion process is done by changing different bits value at different locations. So suppose we have a malicious service provider like SPJ. After receiving the database, he make a pirating of it and leak the database. But our database owner can still extract the exact fingerprint and accuse him for the data leakage. And in addition to the security guarantee of fingerprint robustness, we also achieve privacy guarantee. In that case, the adversary cannot really distinguish the value of a specific entry in the database. And in addition to the security and privacy guarantees, we also want to support a high database utility in order to answer SQL queries with higher accuracy and support data mining tasks. Before getting to our scheme, we will first go through some important definitions. So the first one is relational database. It is defined as a collection of T tuples, each represent a specific person. And each record has an immutable pseudo ID. So in database terminology, this is called the primary key. We are not allowed to change the key. And the neighboring relational database are two databases that only differ by one entry. So it can be the attribute of a single individual. And the sensitivity of the database is just the maximum changeable amount of any entry. In that case, we can define the entry level DP, satisfy the first equation, and M is the randomized fingerprinting scheme. R and R prime are two neighboring relational databases, and S are just the set of all the possible output of the fingerprinting scheme. So before arriving at our privacy-preserving fingerprint scheme, we first develop an intermediate step. It is called bit-level randomization, and we list the design principle here. So we first notice that all the fingerprint scheme essentially conducts an XOR operation between the insignificant bits and random binary marks. And there are randomization steps in the fingerprinting methodology. So the selection of the bits and also the value of the binary marks are random. So that inspires us to leverage the randomness in the fingerprint insertion and to transform that randomness into a certain level of provable privacy guarantee. So we have this conclusion says this bit-level randomization scheme will randomly select some bits of the data and change their value by XORing their bits value with random binary marks. These marks satisfy this probability distribution. And given a relational database with a fixed sensitivity, this scheme preserves our proposed epsilon entry level DP if it only marks the last k bits, and k is determined by the sensitivity value. And those marked bits taking value 1 with probability p equals to that quantity. So that probability is also related to the number of k last bits and also our privacy budget epsilon. Then here is our epsilon entry-level DP fingerprinting scheme. We first collect all the fingerprintable bits in this set. These are essentially all the collection of all the last k bits of all the data entries, and n is the number of rows, and the k, the last one, is just shown in the previous slides. And the key step of this scheme is to first generate a fingerprint, which is a random binary bit string using some hash function. And then we will fingerprint each entry in this set if a specific condition hold. And this fingerprinting insertion is essentially the exclusive operation between the bits and the binary mark. And the condition is carefully designed such that the probability of the mark bit equals to 1 has exactly the same probability in the previous theorem. Okay, so in the paper, we also conduct extensive mathematical study between the connection between privacy guarantees, security guarantee, and the fingerprint robustness, and also the database utility. So in particular, we derive all the closed form connection between each of the block. In particular, for the robustness, we define a different metrics when the fingerprinted database is under different attacks. For example, the adversary may randomly change some of the bits with certain probability. They may randomly remove a fraction or a subset of the database, or they may infer the potentially fingerprint locations by taking advantage of the data correlation. And for the database utility, we not only study the generic utility guarantee, for example, the accuracy, we also study statistical utility like the marginal distribution or joint distributions. But here, we cannot show the mathematics equations here, but if you are interested, you can refer to the paper. Another important concern when applying differential privacy into the real world is the cumulative privacy loss. So it says the privacy will degrade linearly if the same statistics are calculated and repeatedly shared. So this is the same for repeatedly releasing a database under differential privacy guarantee. And we want to control the cumulative privacy loss in this process by using the sparse vector technique. So it only will release a noisy result, for example, a noisy database, when it is beyond some noisy threshold. And this SVT technique will only pay the cost of privacy only when the query satisfies some condition. So this is a general condition for SVT. A randomized function applied on a database plus some noise is larger than a public threshold gamma plus another noise. So as long as this condition holds, we can release this database. And this is the design principle of using SVT to address the cumulative privacy loss. Suppose we want to share the database with capital C different service providers, and our idea is to only share those fingerprinted copies with certain security and privacy and robustness requirement. And recall we have a figure build the connection between different components, utility, robustness, and privacy. So this requirement on the privacy and robustness can already be quantified using the database utility. So this is the figure I'm talking about. You can already go from the database utility to your desired privacy and robustness guarantee. And in particular, we consider this randomized function. So this is the differences between the fingerprinted database and the original database. So this matrix 1-1 norm is just a summation of all the absolute value in the matrix. And you can build the connection between this function with your privacy budget epsilon, the randomization probability P, and also the fingerprint robustness against the different types of text. Then this is a key step of using SVT to address the cumulative privacy loss. So still we will first just generate a copy of the database, MR, under some privacy budget, and then we generate two Laplace noise, one with privacy budget epsilon 2, one with privacy budget epsilon 3. And we will only share this fingerprinted database if the matrix 1-1 norm plus the Laplace noise is larger than some public known threshold plus another noise. And we can prove that this process is essentially epsilon 0, delta 0, entry level DP with epsilon 0, delta 0 showing here. So now we are ready to apply our proposed scheme on the sharing of real databases. And we consider two databases. One is a nursery school application, has about 1,300 records. Each has 8 character attributes and can be classified into 4 categories or 4 groups. And the second one is a census database, has about 3,200 data records, and each have about 14 discrete or categorical attributes. They can be classified into 2 groups. And to insert the fingerprint, we will first encode all these discrete or categorical attributes into integers. And in the paper, we compare with 6 baselines. The first is data perturbation using LDP, then followed by fingerprint. So this is the sequential method, first using a local defined privacy, and then on top of that, inject some fingerprint. The second one is differentially-private database synthesization, then followed by fingerprinting. The third one is the k-anonymity-based scheme to protect privacy, and then add a fingerprint. The fourth one is existing work that conducts a similar study with us. And we also compare with other 2 baselines. The first is just LDP. It does not have any liability guarantee. The second one is the fingerprinting only, so it does not have privacy guarantee. In the experiment, we consider the bit string the fingerprint bit string has 128 bits, and we let the receiver randomly change 50% of the bits in the received fingerprinted database. And in this canvas 2 figure here in the y-axis, we plot the general accuracy of the fingerprinted database. The higher, the better. on the y-axis, we calculate the match of the extracted fingerprint of the compromised database using the random flipping. So the match between the extracted fingerprint and also the original fingerprint. Also, the higher, the better. If there are more matches in the extracted fingerprint string, then the database owner will know that with very high probability, this specific service provider are the one who leaks the database. So the higher the y-axis, the better the fingerprint robustness. So general, to have a higher utility and also higher fingerprint robustness, we want to have some mechanisms that are at the right upper corner of the canvas. And you can see our scheme represented in the red circle, basically all cluster at the right upper corner for both the nursery school and also the census database. And we also study the task-specific applications on the fingerprint database. So we study the SVM classification and the principal component analysis. So for these two specific task-dependent application, we consider, for SVM, we consider the utility as the accuracy loss. So do the classification and calculate how much utility accuracy loss you are experiencing. So also the lower, the better. For the PCA, we consider the total deviation. So we first will extract the principal components of the fingerprint database and then measure the deviation with respect to the original component. Also, the lower, the better. Our figure, our plot, our mechanism colored in red also achieves the lowest accuracy loss and the total deviation in both SVM on the census database and also the nursery school database. So in conclusion, we have developed the first privacy-preserving database fingerprint scheme to protect the privacy of the data when you share the database and also prevent illegal redistribution. We theoretically connect the privacy guarantee, fingerprint robustness, and the database utility together in closed-form solution. And we apply the sparse vector technique to control the cumulative privacy loss during repeated sharing. In the future, we are going to augment our proposed scheme to defend against the correlation attack, where users may take advantage of the data correlation to infer the potential fingerprinted locations. And we will also improve the final database utility by using the data distribution of the original database. And finally, we will also try to make our scheme be robust against membership inferences attack. And so that is all for my presentation. I'm happy to take any question. Thank you.
I'm familiar with the differential privacy approach, not so much with the fingerprinting, but I like the way you explained it. My question is, if you want to extract the fingerprint for the purpose of attribution, is this an illegally distributed copy of my database, for example? Do you need the original database to be able to do that?
No, we do not need the original one. So remember, for the database, we have a primary key, which represents each specific user. And we will use the private key, the primary key of the data record. That will be the seed. There's a random seed when you generate a random sequence. If that seed is fixed, then you will know for a compromised database, you will know which location to check, which location to extract the fingerprint bit. And once you do, you just compare with the original one.